Extra review for quiz. This video goes with the extra practice note sheet located on my website. In this video, I will graph using intercepts, graph using a table of values, and do an example word problem using intercepts. I would recommend that you try the sheet on your own first, and then watch the video to see my examples of how to do the problem. This video is intended to use as review for the quiz. I've just finished the video and watched it, and unfortunately, there's a lot of background noise, so my apologies ahead of time. Example 1, 3x minus 4y equals 12. The problem says to graph using either method, either a table of values or intercepts. Personally, I'm going to use intercepts because y is not isolated, so intercepts will be easier for me. I know that the x-intercept is located along this axis, so it will always be a number comma 0. So to find the x-intercept, I'll substitute 0 in for y. When I substitute 0 in for y, I get 3x minus 0 equals 12, and when I solve that, I get x equals 4. So my point is 4, 0, and I can graph it going 4 units to the right. My y-intercept is along my y-axis, so I don't go to the left or right at all, but I do go up or down. That means that I'm going to have 0 for my x-coordinate. So I'm going to substitute 0 in for x. And when I do that, I get 3 times 0 minus 4y equals 12. So I get y equals negative 3. That means my ordered pair is 0, negative 3. And I can graph that by going 3 units down. Now I can draw a line that goes through those 2 points. The last step is to label my line with the equation 3x minus 4y equals 12. The advantage to using intercepts was that I didn't have to do any isolation, and that zeros are easy to work with. Now I'll graph the same equation using the other method. That means I'll use the table of values. The first thing I need to do in order to graph using a table of values is isolate y when possible. So in this case, since I want to isolate y, I subtract anything that is not attached to the y, so I subtract 3x from both sides, leaving me with negative 4y equals negative 3x plus 12. Then I divide by the coefficient because we want to undo the multiplication, and I'm going to divide every single term on the right-hand side by this negative 4. That leaves me with y equals 3/4 x, so negative divided by a negative, which becomes positive, minus 3, because 12 divided by negative 4 gives me a negative 3. Now that I've isolated y, I'll set up a table. I have x, and I have y, and for my inputs, I'm going to pick multiples of 4 in order to avoid getting fractions, because my denominator, that's my coefficient, is 4. I'll create a skeleton equation, so I have 3/4 with a blank spot for x, which I'm going to substitute in whatever my x value is, minus 3, and I'll write this for each input. And then I'll substitute in my inputs, negative 4, 0, 4, and 8, and I'll do the calculations in my head using the order of operations, or you can do them off to the side. Be careful with your powers, and be careful with your cancellations. We should get the points, negative 4, negative 6, 0, negative 3, 4, 0, and 8, 3. And it's helpful to write these out to the side. And then I'll graph them. Luckily, they came out in a straight line, which means that I graphed them accurately. So I'll connect them with a line, put arrows on the end, and I'll label it with the equation, either the old or the new one. If they hadn't come out in a straight line, I would look to see if I made a mistake in my table, or if I made a mistake in my plotting. A quick way to check the table is if you have a pattern on the left, such as here we have plus 4, plus 4, plus 4 for my inputs, then I should also see a pattern on my right for my outputs, plus 3, plus 3, plus 3. So I know that my table is most likely accurate, and I would check to see if I made a mistake in my plotting. Those are the two main methods for graphing equations that we've learned so far. The first was to use intercepts. That's when we take the 2 points of where our equation crosses the axes by substituting in 0 for x in order to find the y-intercept and 0 for y in order to find the x-intercept. The other is to use a table of values where we choose the inputs and we get out outputs. In order to do this, we need to isolate y. The last thing I'll do in this video is an example of a word problem. This says you go to a carnival and start with 35 tickets. For each ride you go on, you must spend 5 tickets. Write an equation for how many tickets you have left after X rides. In general, I'd like to start my equations with y equals. So my y is going to stand for the total number of tickets I have left. I start with 35, and after every ride, I subtract 5. So I want to see if this makes sense. Initially, or after 0 rides, this will give me 35. After 1 ride, the 35 will go down by 5, and I'll have 30. After 2 rides, I'll take away 10 from my 35. This makes sense, so I can conclude that my equation is correct. I always want to define my variables, because that will help me know what to do on my graph. I labeled X as the number of rides that I've been on, and Y is the tickets remaining. It's important to remember that it's not just tickets, because that could be tickets spent, tickets we start with. This is how many tickets we have remaining. I've gone ahead and found the X and Y intercepts. I found that the X-intercept is 7 by substituting 0 in for Y in my equation and solving for X. And I found that my Y-intercept is 35 by substituting 0 in for X and solving for Y. Given this situation, we really only need quadrant 1 because we want to have a positive number of tickets and a positive number of rides. I'll label my axes with things that we defined our variables as. So my x-axis will be the number of rides, and my y-axis will be the tickets remaining. Then I need to choose a scale. In this case, I want my x to reach up to 7, and my y to reach up to 35. So for my x, I'm going to go by ones. For purposes of being able to fit it, I'm not writing every number, but every box is worth 1. And for my y, I'm going to go up by 5s. It's important to remember that if we decide from the axis to our first line is 1, then to the next line must be another 1, and then another 1. And on our y-axis, same thing. If from the origin to our first line is 5, then we must have 10, and then 15, and then 20, and 25, etc. I've graphed both of my intercepts and have connected them in a line. Depending on the situation, sometimes we extend our line with arrows, and sometimes we don't. I know that I can't go on a negative amount of rides, and I also can't go past 7 rides because then I won't have any more tickets, so I chose just to graph in quadrant 1. A lot of times you're asked what your intercepts stand for. Our intercept 7, 0 means that after 7 rides, I have 0 tickets remaining. Notice that I addressed both my x and my y here. Similarly, the y-intercept 0, 35 means that when I've gone on 0 rides, I have 35 tickets remaining. And I could pick any other ordered pair, for example, the point 5, 10, and I could determine what that means. That means that after 5 rides, I only have 10 remaining tickets. This concludes your review video for the first linear equations quiz. Thanks for watching.